So today we will conduct one experiment on capacitor. So we'll study the charging and discharging of the capacitor. So the aim of the experiment is to study RC series circuit and to determine time constant of the circuit. So the apparatus required for this is RC network, DC supply 0 to 30 volt, variable, then stopwatch, CRO, probes, and links. So here we will use the IIT Bombay virtual lab platform to conduct this experiment. So we will simulate this experiment. So before simulating, let us go through the theory part of this experiment. So here we will consider one RC circuit, okay, shown in the figure. I will show just that figure. That figure contains a capacitor C, which is uncharged initially at time t is equal to 0, and it gets starting to charge through resistor R when switch is closed. So let us analyze the charging of capacitor using node analysis method. So this is the theory part. So in this theory part, your VC of t, we consider the loop which constitute your supply voltage, then resistance and capacitor. So if you consider that, then at a node 1, assuming the instantaneous voltage across capacitor to be Vc, so we'll get this equation Vc of t minus Vi upon R plus C dVct by dt is equal to 0. So this is the form of dVct by dt plus pVct is equal to Q, that is the charge. So here P is 1 upon RC and Q is equal to V upon RC. So the solution of this is results into Vc of t is equal to e power minus t upon RC integral e power minus t by RC Vi upon RC dt plus R e power minus t by RC. So k is a constant of integration here. So I will get that Vc of t is equal to Vi k e power minus t upon RC, where RC is nothing but your time constant, and it is henceforth we'll call it as a tau. So at time t is equal to 0, Vct is equal to 0 since capacitor is uncharged initially. So k is equal to minus Vi. So hence Vct is equal to Vi into bracket 1 minus e power minus t upon tau. So at t is equal to RC, when the power of exponent becomes unity, that time I will get Vct is equal to Vi into bracket 1 minus 0.368, and that's come to 0.632 Vi. So therefore, at time t is equal to tau, capacitor gets charged to 63.2% of the final value, and this value of RC is called as the time constant and is denominated by a letter tau. So it is defined as the time at which the response reaches to 63.2% of its final value. The graphical representation of charging of capacitor with the time is shown in the figure. At steady state, charging current for capacitor through resistance reaches 0 and capacitor gets charged fully at supply voltage Vi volt. So here a charging waveform is there. So as time t is equal to 0, V across the capacitor, the voltage across the capacitor Vc of t is 0. But as I closes the switch at time t is equal to 0, the voltage across the capacitor it rises and will reach at time t is equal to infinity to a steady value of a maximum supply voltage, that is Vs. So here we will get the constant steady voltage equal to supply voltage across the capacitor, and whatever the time required for this rising curve to reach to 63.2% of the final value, that is called as the tau, that is the time constant. Now switch is thrown on side B, so capacitor start discharging through R. Now your capacitor is discharged. Now node equation for node 1 can be written as Vct by R plus C d dt of Vct is equal to 0. So solution of this gives us Vc of t is equal to k is power minus t by tau. So to find the integration constant k, we can use the initial condition that time t is equal to 0. I will get VCT is equal to VI. Since the capacitor is in fully charged condition initially, that is at t is equal to 0, that therefore the constant k is equal to VI. So the voltage for which capacitor will get charged can now be expressed as a function of time as VCT is equal to V I e the power minus t upon tau. Now this is if time t is equal to RC, that is time constant, is a discharge time constant with no change in resistance, so it may appear to be same as charging constant. However, if the resistance is varied for a discharging path, the time constant of discharging path is decided by resistance value in discharging path along with value of capacitor C at time t is equal to tau. So Vc of t is equal to 0.368 Vi. So for the discharging of capacitor, time constant can be defined as the time at which the capacitor voltage is 36.8% of its final or of its initial value, right? So the graphical representation of discharging of capacitor is shown here. So here initially my voltage across the capacitor is maximum, that is Vs, and as soon as I short it through resistance R, the capacitor voltage reduces and it reaches to 0 at time t is equal to infinity. But the time constant tau can be defined as it is time required for the curve to drop down to 36.8% of its initial value. So that is nothing but my time constant tau. So here is the circuit diagram. Here the resistance is connected in series with the capacitor across a voltage. Here one switch is there. When the switch position is at A, that time my capacitor will charges through resistor R. When the switch position is at a position B, that time my capacitor will get discharged through resistance R. And across this capacitor, voltage can be measured or displayed on a DSO. So in the next lecture, we will simulate this and we'll view the corresponding waveforms for this charging and discharging of the capacitor. So thank you very much.